All right. Welcome everybody. This is exciting. This is our last webinar of 2023. So we're pretty excited. We're taking a break for the holidays. And then we're kind of rethinking what we're going to do for next year. We have some really exciting stuff in development for next year. So more on that. Stay connected with us because we are going to do some really great stuff moving into 2024. But for now, in this webinar, we do have a very special focus today entitled Real World Robotics. And you'll see you're visited or where we have a guest joining us today, Drew Patel, who we will introduce in a moment. In the meantime, you can kind of just, say hi to him, give him a thumbs up, give him a wave. You may only be able to see half of his face. There might be some technical issues on his computer. I'm not exactly sure. But yeah, bear with us as we get things rolling. So let's go ahead and kick off this webinar. So great. As always, and let me back up. As always, we really strongly encourage you guys to connect with us. If you have any questions along the way, along this webinar, you can always drop them in the chat. However, if you want to connect with us outside of the webinar, feel free to send us an email, info@ubtecheducation.com. That email address can always be found on our variety of social handles, as well as our website, ubtecheducation.com. We are on all the major social platforms under UBTech EDU, except for YouTube, which is UBTech Education. So check them out. We post all the stuff we'll be doing and that, all the new stuff that's coming up. So be sure to like and follow us and, connect with us along our journey. So probably most of you guys have been with us before, but if you haven't, my name is Rusty and I am the Education Product Manager for UBTech Education. I am joined with my colleague, Christina Davis. Christina is feeling a little under the weather, so I'm not going to put her on the spot, but if you do want to say hello, feel free.
Sure. Hi, everyone. I'm going to be monitoring the chat and the Q&A. So if you have questions, make sure you add them into the Q&A and feel free to say hello in the chat.
Great. Excellent. Thanks, Christina. Great. So we'll just dive in. So I do want to give you guys a warm welcome to Drew Patel, someone that I work pretty closely with here at UBTech Education. He is going to kind of lead us through his own little presentation about using the engineering design process at work. So without further ado, let me kick it over to Drew.
Hello all, thank you for having me. It's a pleasure. And now what I'd like to first talk about is how I got to where I am today. So my background is actually in mathematics. I was teaching STEM for a while, purely theoretical and very academic in that sense. But in the last, I would say just pre-COVID, I got some exposure to robotics via the VEX competitions, the VEX IQ, as well as Raspberry Pi projects. So what that led to is me realizing that all this theoretical knowledge, it works only in a hypothetical sense. And when you bring in real life and you bring in the practicalities that are demanded by businesses and consumers, what comes into play are variables that need to be taken into account, such as if you were to look at the VEX robotics competitions, they require timing, they require materials constraints, there are timing constraints, as well as compute constraints. And therefore, what something like that teaches someone with a very theoretical background is the realization of the design process comes into play, because that where I wasn't quite used to thinking in that with that mindset. And so starting through the VEX competitions and Raspberry Pi projects, it really led me to figure out how to think in a certain way so as to work towards real practical engineering solutions instead of simply very theoretical models. And so today what I do is I take inspiration from my background in formal mathematics, in Vex Robotics, designing STEM curriculum and lab work to figure out now. If you were to switch on to the other slide, Rusty, what I do today is I work on medical grade disinfection robots. So Adibot, uh, the way we troubleshoot and work with the whole team brings into play this design process where we work with very complex medical grade teams that need to deploy these robots, want to deploy these robots, or perhaps are not quite sure if these robots are for them. So then this whole process is now uh, applied and implemented so that to first figure out what exactly is the problem here, because especially where we are in the United States, the labor is quite an integral part of every workplace, and especially in the medical business, especially large institutions such as Cedar Sinai, Mayo Health Clinic, even the best of the best hospitals in America have a labor shortage. And so, what our robots are able to do is help executives find the gaps and help them fill them at a cost that is quite reasonable. So, in that sense, a particular solution might be to fill in that labor shortage gap. In other places, because of complex architecture, the problem initially is about how do we figure out disinfection for specific pathogens due to their interior structures, due to their the overall constraints are quite varied. And so this whole process gets reiterated again and again and again until we are able to deploy a robot successfully. And so this mindset really scales very well, whether it be a VEX robotics competition or whether it be a large medical institution that has consequences of very large scale uh, infection prevention, as well as very large scale events that can happen due to the gaps in disinfection or gaps in labor. And so if I were to go over a little bit of my current role with the Adibots, what I'd like to highlight is what the robot actually is, because then what I can do is come back to this design process based on the constraints I have. So if you were to look at your screens, the Adibot robot is quite a complex autonomous disinfection solution. It has a variety of sensors, which some of these sensors might be familiar with you if you've played with our products, UKITs, as well as if you have been in if you've been reading about recent news in robotics. So one of the key features is a LiDAR sensor on top of the robot. There are ultrasonic sensors on the robot, as well as RGBD depth sensors. So this robot provides a suite of safety as well as vision solutions that are tied together so that the robot is very well capable of navigating as well as providing disinfection and providing full transparency on the process itself. So what you're seeing at the bottom of the screen is a LiDAR map that the robot generates, and the user has to plan using the design process to first start with the problem, whether it be a specific pathogen that needs to be eradicated from that facility, whether it be just to fill a gap in labor shortage, or whether it is a certain architectural and interior design issue that the robot has to now cater to. So in what you're seeing on their screen is a LiDAR map, and what the user did was plan disinfection times and points for the robot to navigate to, and then find a path for the robot to, or help the robot find a path to the charging dock, all, and so that this process can be repeated again and again and again without any hurdles or gaps in workflow. And so if you were to go back to the engineering design process for a second, so if I were to now bring this robot into play, and if we take the case of one of the pilot programs we did recently in Arizona, Phoenix, their issue was a C. diff pathogen issue, which is a very, very tough pathogen to disinfect for. And chemicals can only do so much. And therefore, what this robot needed to do was go into OR operating rooms after surgery has been performed, and after manual cleaning was done, the problem was how do we time it correctly so that the robot goes into these rooms, attacks high touch areas that are usually where C. diff lingers, disinfect that space, fully autonomously navigating from point to point and finding itself out of the room, going to another OR, and then disinfecting that space, all while adapting to changing structures, with rooms being populated with machinery that changes all the time, that is dynamic, and as well as helping the managerial staff keep track of when the robot performed what action, and while syncing correctly with the workflow of the janitorial staff. And so if we were to think about the mindset that is required to not only plan, but also create a solution that is quite appropriate, it takes a lot of trial and error. It takes a little bit of time investment to first understand the constraint. So in our case, firstly it was understanding what the pathogen is, how it needs to be disinfected, what it takes to disinfect, whether it be the energy levels, whether it be understanding a little bit of the chemistry of the pathogen, as well as understanding the layout of the hospital, and then layering on top the capability of our robot. So no robot is a perfect solution. What we have to do is plan accordingly based on the constraints of not only the robot, but also the circumstances and the environment it will be placed in. And so with our robot, we know the computer vision models are quite capable of understanding the space it is put into, but then the problem is timing it all correctly. And so the disinfection times have to be made and set up correctly so that and as well as taking into account the navigation time for the robot. So the robot has to travel from its charging dock, go to its disinfection points, to a variety of rooms, all while controlling the speed, controlling the exposure time using UVC, and then making its way back, and then seamlessly fitting into the workflow of the hospital so that the OR is ready in the morning for doctors to perform surgeries in. And so this mindset is extremely critical. And I look back on my days of Vex Robotics on educational curriculum design, as well as the small projects I did, because all of that scales. Even a simple idea of a simple toy RC car, or perhaps even a robotic arm that we will talk about in a little bit, it all scales. All you do is start from the very bare bones of an engineering problem and then add complexity layer by layer. But nevertheless, what you're following is the same process again and again and again, whether it be a middle elementary school student trying to just lift a ball from one place to another, whether it be moving a car from one side of the room to the other, or whether it be the Tesla autonomous sedan trying to navigate across highways and changing lanes while communicating with different cars. And it's the same process, reiteration, with adding layers of complexity based on the application.
And Drew, if I could jump in for a moment, because I think you're saying some really great things, but to provide a little more context, excuse me, the robots that Drew is currently working on, these are self-navigating, autonomous disinfection robots that disinfect environments using UVC lamps and technology. So for kind of in layman terms, they are autonomous robots that go from room to room based on the way that they are programmed. And they utilize these lamps that you'll see in these images to disinfect utilizing UVC. So they're really interesting and cool robots, and great for particular environments like hospitals, or large schools or whatnot that are trying to disinfect larger areas very efficiently. So I know what how Drew is making this connection back to the EDP is amazing, because exactly what we're trying, the mindset that we're trying to instill with students that are utilizing the UKITs, is the same mindset that Drew utilizes to solve these really large problems. And whether if it's robotics or if it's just any sort of problems that we're trying to solve on our throughout our day, utilizing this framework of identifying the problem and moving through that EVP is still very, very applicable. But I just want to provide that context because I know when we start talking about the autonomous disinfection robots, it can seem a little daunting, especially if you're unfamiliar with this sort of technology. And also we should also make the connection that the same company, UV Tech Education, we are also partnered. We have a enterprise division where we create and work with these particular Adibot disinfection robots. So that's why Drew and I are pals. We work on both sides of the coin here. So we work on education robots as well as disinfection robots.
Exactly. Thank you, Rusty.
Of course, I'll throw it back to you, Drew.
Thank you. I think at this point, basically, what I wanted to highlight in terms of the enterprise side of my current role, I think is quite. I think I've made that point, and I don't want to spend more time on it. But what I did want to highlight is the technology scales. The problems, when you break them down, are still very basic, and all you're really doing is just the application. It changes, and so you bring in more complexity. But the very bare bone problems is still the same. That's where what I'd like to really emphasize.
Mm-hmm.
So if you were to go on to our next slide. So this is an example of what I deal with when it comes to implementation of these robots. So this robot has to navigate complex spaces in an environment that is extremely dynamic, dealing with obstacles and features of a room that are quite that are ever changing, that are quite hard to predict. And what we have to do on our side is help the customer understand what the robot is capable of to implement it correctly. And so in our case, in the case you're seeing on your screen right now, is an OR that has been set up for a certain kind of surgery. And what I had to do for this customer was help them plan disinfection accordingly, so that even if the room changes, the robot is still able to disinfect correctly again and again, no matter what the layout ends up being, no matter what machine is in or out of the room. And when it comes to trial and error, this was part of my trial and error process in setting up the plan for them, where the UVC lights didn't come on in this clip because I turned them off, and all I was doing was testing the navigation of the robot. And so I probably did, I want to say, 10 runs. And what I had to do was figure out exposure times, and in this case, also look at the layout generally from a top-down view to figure out what is the basic layout that is going to repeat again and again, what layout patterns are going to be repeated, and then plan the path accordingly. But just to highlight how this robot works, and bring it back to also the UKITs, the basic sensing technology is still there that is found in UKITs, to be honest. So the ultrasonic sensors, the IR sensors are simply a more complicated and more advanced sensing technology that is in these robots, but it still starts from the science is still the same of the ultrasonic and the IR sensors that are found in UKITs, where it is still sound waves bouncing off of obstacles to help the robot navigate, to help the robot ascertain what is in front of it. The only difference is the amplitude and frequency of these sensors change as you scale up, because the consequences of the robot not functioning correctly are quite dire. But the science is still the same. The basic bare bones idea of what these sensors do uh, in a technology stack like this one is still very much in parallel to what a simple UKIT robot can do, which we'll highlight on the next slide. So, like I mentioned, bring it back to the screen before. It's quite having a certain frame of thought that you abide by is quite important when it comes to robotics, is because it can get out of hand when you try to simply make a robot. So when you don't have a framework, when you don't have a certain disciplined way of thinking about solutions, it's very easy to just look at a problem and just go at it, brute forcing your way through to find a solution by doing 100 trials, and it's very time consumes. The time consumption can be quite massive when you don't have a very disciplined framework for solving certain problems. And so when we look at a very good when you've practiced enough and have repeated processes in place that are repeated, scalable, what that leads to is a very efficient problem solving overall time frame. So in my case, it still comes back to the same framework again and again, because what I'm able to do is not really feel a certain pressure to solve a problem. All I need to do is break down the basic issue at hand, break down the basic idea of what it is that I'm trying to solve, what it is that I can repeat, what it is that I can what is that I can actually work with and repeat and try and repeat and try again, and then over perhaps even 5 iterations, I can solve the issue at hand. And that all comes down to even a simple middle school problem, perhaps, that will highlight 2 robots from our UKIT program and bring it back to the same idea of if how a student might want to think about it as well. So if you were to, I wanted to show an example of an industrial robot, because partly this call is also about connecting the dots between the classroom and where we are currently. So what you're seeing right now is one of the smartest robotic arms that's available when it comes to industrial robotics. So just say, I would say 5 years ago, industrial robotics was quite static. So cars would get welded by robots, foods would get packed by robots, for sure. Absolutely, robotics have been around for a very long time. But the difference is between robots that can adapt and robots that cannot adapt or quite fixed. The program is quite fixed. So in this case, what you're seeing here is a robot is able to use its vision to pick apart a certain box of nails, a certain box of pieces based on pattern recognition, and there's a whole layer of technology built in so that the robot can be implemented without worrying about uh, a mixed batch of stock. And so, bringing back to the next slide, our UKIT robotic arm, the basic idea is still there of an engineering a robotic arm. So what that all you're doing is figuring out what it is that will make the robot adaptable. So first, it comes down to figuring out how can a robot lift something efficiently again and again and again without breaking down. What can we make sure that How can we make sure that this robot is stable under load? What are the load requirements that so that will affect the kind of servos you use, how the amount of servos you use, what is the workspace angle. So in this case, this arm was designed to simply rotate across one lever arm and sorry, 2 lever arms, and so that will affect the articulation, how much of a working space a robot will require. And so if I were to connect it back to the industrial robot, what we're looking at is a lot more articulation. All that means is you're adding more joints to the arm. And what that does is the robot can move around more freely, can adapt to a variety of workspaces, and can also be quite flexible. So in our case, if we were to go out to the robotic arm, and on the left side of the screen, what you're seeing is a basic program for this robot, which only involves moving servos, which in itself is quite capable. So if you look at the factory robotic arms from 10 years ago, that's all they were doing. The engineers would program the robot to move a certain way again and again and again until they figured out the right degree of rotation they needed, and until they figured out the right distance that robot needs to cover, and then it was repeated. That's why there was something called error rate when it comes to production outside. When it comes to cars that were being released by all these automakers, there's always an error rate, and then the manual labor has to come into play to make sure the production is correct. So now with adaptable robots, what all you are doing, or all the companies are doing now, is figuring out this old idea of a robotic arm that can do something based on a simple programming sequence. But the AI part is helping the robot find the error. So given, say, a piece of metal is 1% bigger than the last, the robot can now sense, whether it be using LiDAR, whether it be using a simple camera. All the algorithm is doing is running through a sequence of millions of images it has based on the patterns it has learned to figure out what is the differential between the first and the second piece, and adapting. But the basic idea is still the same. We're still coming back to the basic idea of what do we want to solve, and then adding layers of complexity to make sure we have a high success rate. So we don't really need to be worrying about we don't need to be overwhelmed by the complexity. All we have to do is figure out what it is that we're trying to solve and go at it again and again and again, adding little layers of complexity little by little, and we end up with a great solution over time. So it's never a one step to 100% practical solution. It's always a staircase of thousands of steps. I wanted to also highlight a second example from real world robotics as we're talking about it. In this case, what we're seeing is an Ocado robot facility. So what this facility does is fulfill grocery orders. It's fully automated. And what you're seeing are basically cars of robots, or sort of small pickup trucks, going back and forth, picking up, dropping off. So under the robot are boxes for orders. And so it's layers and layers of robots stacked on top of each other, and based on the orders that have been programmed or that are being fed into the system, the robot fetches things, drops them in, fetches, drops them in, fetches and drops them in again and again. Now, the complexity is quite large. There are thousands of robots, all so many moving pieces. But the basic idea is we want a robot that can pick something from one place, drop it in another place, come back, pick up something else, drop it in a particular location. So the basic idea is just that: pick up something, drop, go back, pick up something else, drop it again. And that brings me back to this idea of one of our robots on the UKit app. This is part of the intermediate kit, but it can also be adapted to a more advanced robot. But the idea is still quite simple. We can add sensing technologies such as the ultrasonic sensor, the IR sensor. We can add LED sensors that come with UKit as well, or even the impact sensor, as I like to call them. They're switches, but all they're doing is you can build a loop, and what the loop does is help the robot recognize what it needs to do next. So in our case, the robot has to go somewhere, the sensor can activate the next task, and then at the next location, another sensor comes into play, feeding the robot guidance and processes that can run all simultaneously. And that complexity can be added by someone in middle school quite easily. And what you saw earlier was just a much better, highly capable system, but the complexity layers are only incrementally added onto it. The basic idea is still the same, that is very much a problem even a student can solve. And so the idea is to just break down a problem, run through the process again and again and again, and really understand what is the bare bones of what you're working with and what the constraints are, instead of being overwhelmed by the advancements that you may see on YouTube or the viral moments that go around in the world of robotics. But starting from scratch, starting from the very bare bones, can easily lead to great robots and examples of great complexity that on surface may seem quite overwhelming. But trusting the process and trusting and developing the right mindset is really key to creating amazing things.
Yeah, absolutely, Dhruv. And you're getting some props for the nice connections for sure. I think it's you know, it's not easy to make those connections. I think, especially adults, you see these really, fancy, large robotic systems doing really complicated things. And it's hard to make the connection that what the students are doing, could be connected to those complex systems, but it's all comes down to that mindset and that approach, which is the largest connection in the single driver to creating these really large, these different systems that are solving these complex problems. So kind of pulling apart, literally pulling apart those wires and those pieces to kind of think about how logically we can put them together back together to solve specific problems is so important, and it really does all come down to that mindset, and that it really is one of the biggest goals that we are trying to achieve with our robotics kits, with our curriculum, and also through how we work directly with educators, on the professional development side, is to really put a strong emphasis. And I know a lot of probably, preaching to the choir here because we have a lot of STEM enthusiasts and STEM teachers that have joined us, but this is kind of that basis for project-based learning, for STEM educational theory, is really trying to build that mindset above everything else. So regardless of the tools that you're going to use, or the lessons that you're trying to teach through the systems, it's all about the mindset that you're going to utilize to solve that problem. That's what we're really trying to get through. And I think, Drew, you did a great job making those connections, back to through all the different steps. I mean, you're solving really cool, really important questions using technology, but you're still using those same systems, the same steps that are, third graders up through our high school kids are utilizing. So thanks for sharing, Drew.
Absolutely.
Great. So a couple of things. We're just going to kind of wrap up. I do want to point everyone back to our training site. If you want access to our training resources, we have a few training courses. All of our webinars, we're going to link this webinar there as well. We also have curriculum. You can contact us directly through our training portal. So don't forget it's there. This, of course, can be linked through our website, ubtecheducation.com. We do have some time for some Q&A. If you guys have any questions, want to ask myself, or you want to ask Drew anything, we'll pause for a moment. Drew and I can do a little dance or do the robot or something while some questions come in. I don't know. But yeah, feel free to to drop them in the chat. Otherwise, while you think of any questions, just a big reminder, this is our last webinar for the year. We're going on, our holiday break, and then we're coming back strong into 2024 with some really exciting new stuff on the horizon. So please stay in our network, stay close to us, because we have some really exciting and some big news coming up next year. So if you're not signed up for our newsletter, what are you guys waiting for? Go to our website, sign up, stay in the know, connect with us on all of our platforms, etc. So great. So we don't have any questions, which is great. I don't, that means that we just covered everything and everyone is clear and you guys want to get some time back. Well, huge thank you to Drew. Really appreciate you taking the time and thinking through how to share some of your perspectives with us. So big shout out to you, Drew. Thank you. I owe you a coffee or something. So great. And thanks for everyone.
So much for having me. It's been a great exercise for me as well, because you learn so much more when you try to talk your thoughts through, because you have to really think about how to think. And so it's been a great exercise for me as well. So thank you so much.
You got it. Anytime, Drew. We'll see you next month. I'm just kidding.
Absolutely.
Great. Thanks everyone for joining. And yeah, everyone have a great rest of your evening, day, wherever you are. And yeah, see everyone soon.